Hi, I'm Manabendra. Today I'm going to talk about constraint analysis. I have already made one presentation on constraint analysis and I'm going to continue on that. So last time I introduced given a Lagrangian in the case of point particle dynamics, in the classical dynamics, how do you know if there exist constraints in the system? So what I was talking before was that you have a Lagrangian which is a function of q, qn and qn dot. It's the configuration space, and we have found one condition for which we will know whether there is constraints in the system or not. So constraints we are going to define in this fashion, where is function of qn and pn, where qn is the generalized coordinates, pn is the generalized momenta or the conjugate momenta with respect to the qn, which is defined as del L by del qn dot. So having constraints mathematically mean there exist functions of the generalized coordinates qn and p and generalized momenta pn, meaning that not all momentas are independent. Not all momenta are independent. So if you pictorially, if you have twice n dimensional phase space, so this represents qn, this represents pn. So there will be a hypersurface on which the system is constrained to move. So the dynamics is contained on this hypersurface. All right. So the general formulation of Hamiltonian dynamics, which says qn dot is equal to del h by del p, and pn dot which says minus del h by del qn doesn't work. Why? Because not all the momentas are independent. In this formulation, the constraints are not taken into account here. So we have to find out a mechanism that takes care of this constraint or this hypersurface, to speak geometrically. So that's what we are going to see, and today's session will be basically on the classification of these constraints. All right. So the constraints of this kind are we are going to call them as primary constraints. Primary because they do not include any sort of equation of motions, meaning that they are basically some kinematical relations on the phase space without invoking any equation of motion, Lagrangian Euler-Lagrange equation or any equation of motion yet. So we are going to see how to formulate the dynamical laws of motion when we have constraints in the system. So a quick look how we arrive at this is we have to vary this quantity Pn Qn dot minus L, where L is the Lagrangian, and if you vary this quantity, we'll see that it depends on only this quantity. If you name it H, it depends on only Q and P. That means the variation this turns out to be Q del Pn. All right. So, and we are going to say this quantity to be Hamiltonian, but this Hamiltonian H is not unique. For example, if you have a Hamiltonian, say for example H Q comma P is a function of the Qn and Pn, and if you add any linear combination of your constraint, say Cm phi m, define a new constraint, a new Hamiltonian, say it's H star, then this constraint, this Hamiltonian is as good as the old Hamiltonian, because phi m is weakly 0, because phi m are the constraints, they are given by this equation for the hypersurface. So if you add any linear combination of the constraints, where m going from 1 to m, that's the total number of constraints present in the theory, then the dynamical laws of, or the dynamics or the physics or the Hamiltonian cannot be distinguished, the new Hamiltonian cannot be distinguished from the old Hamiltonian, writing in this fashion, because essentially this is 0. Now if we take this into account, then the new equation of motion can be written as, taking into consideration the constraints, the new dynamical equations look like this. So I stop here and take another part. Let's look at the structure of Poisson algebra. So the Poisson bracket is defined as comma z, where f functions of q and p, and so is z is a function of qp, could be any arbitrary functions on the phase space. Then the Poisson bracket of f with respect to z is Poisson bracket of f comma g with respect to q and q comma p is defined as del by del q del by del p minus del by del p del by del q f z z f c. So this is how Poisson bracket is defined. Now let us look at some properties of Poisson bracket. Minus f comma z This is antilinear. Oh, sorry, this is antisymmetric. Metric. Just if we flip them, we get a negative sign, and it's linear in either number. So f1 plus f2 comma z is f1 comma c plus f2 comma c. So this is the linearity property of the Poisson bracket. Thirdly, we have the product rule. f1 f2 comma c is f1 f2 comma c plus f1z f2. It's a product rule. Then finally we have the Jacobian identity, which says f z comma h Poisson bracket of g comma h with f, then the cyclic permutation that makes it z h comma f, then h f comma z, the sum is equal to 0. That is our Jacobian identity. All right. Now, why I am writing all these properties? Because somehow I want to write my dynamical laws in a very compact way. Now, it can be shown that if we use these properties here, there is an advantage of writing these dynamic laws in a very, very compact way. So, one of the features of Poisson bracket is that if you want to include anything into the Poisson bracket and still you want to say that it is well determined, well behaved, then any functions that can be included must be of the form, must be depending upon q and p. But this sitting here are quite unknown. They may or may not depend on the phase space variable. So we cannot just right away put them inside a Poisson bracket. Of course, we can do that, keeping the properties of, if you agree to keep these properties of Poisson structure intact, and then we can possibly include this the unknown coefficients. But what will happen is that when they are not functions of q and p, the Poisson bracket will not be determined. Let me give you this with an example. For example, any functions that depend on the phase space q and p, we can write from here. It is easy to see that dz by dt, that's a total derivative of g, can be written as z psi m. So the equation of motion can be written concisely in the form of Poisson bracket. But now if you consider these properties, that is antisymmetric, linearity, and the product rule, and let us extend the meaning of the Poisson bracket by saying that at least this holds good, whether or not we are not bothering about whether the coefficients are functions of q and p or not at this moment. Then using these three properties, linearity, product rule, and the antisymmetry, one can write z h plus um psi m as c comma h plus um. So the right hand side is nothing but, so it says z dot can be written as z comma h t if we define h t to be h plus um. The advantage is that the coefficient um, which we do not know, could be a functions of q and p. If they are not functions of q and p, at best this is not well defined. The Poisson bracket is not well defined. But if you look at on the right hand side of this equation, um is sitting outside the Poisson bracket and phi m are all 0. Phi m are all 0. Therefore, there is no harm in writing and defining the total Hamiltonian in this way and including everything in the inside the Poisson bracket. So now the next thing we are going to look at is the consistency conditions on this equation of motions. There are a couple of possibilities. For example, the physical argument behind this consistency equations are, since this phi m are, all phi m's are 0, weakly 0, and if they have to behave as a constraint, their time derivative as well should be 0. Otherwise, that will be not constraints. Meaning that if it's a constraint at this moment, it should be constraint for all the time. So what can happen is that maybe we turn out to get 1 is equal to 0 from this equation. For phi m, if you find phi m dot is equal to 0, and if we impose this, then maybe we are getting something 1 is equal to 0. This could be possible. One example is if the Lagrangian is for example q, then the Euler-Lagrange equation to get is 1 is equal to 0 kind of thing. So that is not consistent. That means actually our starting point itself is not consistent. So Lagrangian cannot be any arbitrary functions. For example, L is equal to q is giving us some inconsistency at the level of the equation of motion. So, okay, we are not talking about that. So straight away we have to remove all this kind of Lagrangian, which is not physical. Okay, then the next thing is what you are looking at is this equation psi m comma h plus um prime psi m prime. So the next possibility is that we get something which are independent of these coefficients, but q comma p is equal to 0. Now there are two possibilities. Either this new function is a linear combination of our primary constraints. If that is so, we need not worry. We are not getting any new constraint. And if it is not, if this x, which is a function of q and p, is not, we cannot write, for example, in the linear combination of the primary constraints, then this is a new constraint in the theory. So this kind of constraint we are going to call a secondary constraint. Why secondary constraint? Because we have used the equation of motion to arrive at this. In the case of primary constraint, we have not used any equation of motion to define the primary constraints. Here we have used, therefore we are going to say this to be secondary constraint. Now again, this secondary constraint must undergo this consistency check. They must undergo this consistency check. That means we have to, in place of phi m, we have to put chi there and see if they are giving us some inconsistent result or not. and we need to carry out this process until we are exhausted. So if they are producing any other constraint in turn, we are going to say that as tertiary constraint, and so on and so forth. And again, the tertiary constraints has to be checked with this consistency check, whether they are a linear combination of the primary or secondary constraints or not. If they are and the evolution of the constraints must be 0 at each and every level. So it has to go through the same algorithm. Okay, now the next thing is quite general in nature, where we allow this the coefficients to be functions of q and p. Now if you allow these coefficients to be functions of q and p, so we can always have the homogeneous case for which Vm size A psi m is equal to 0. It's the homogeneous case. So in the most general case, this is the capital Um. So the most general situation is Um is function of plus some linear combination of this, where this is the homogeneous part. So our total Hamiltonian Ht will be H plus psi m plus Vam phi m, where this Va, the coefficients Va are arbitrary in nature. That could be any arbitrary value, and this gives us some interesting features. So this is all about the classification of constraints, and the implications of this arbitrary constraints will generate some symmetries in the theory, and I hope to talk more about these implication of this arbitrariness in my next talk. So today let me conclude that I have shown the structure, the Poisson structure of a constraint system. I have talked about the classification of the constraints, mainly the primary and the secondary constraints, and in the next talk I will be talking about the first class constraints, which are the generators of symmetry. Thank you very much.